when we're dealing with vectors, we can, of course, refer to them in terms of their magnitude and their direction, and we can also put them in standard position and refer to their components. So if we're given the magnitude and direction, we can use trigonometry and mathematics to find the components. So if we look at a vector in standard position, and I'm just going to draw this vector here, call it v, and then we will refer to its direction, of course, and that can be referred to in different ways, like I talked about. Maybe we say due north and the vector's going here, but we want to state that as an angle. And so the way we're going to do that, no matter how the information is given in the problem, we should translate that into the smallest positive angle in standard position, measuring from the positive x-axis to the vector. So this would be the direction theta. Where theta is between, and we'll use degrees, but of course you could use radians, right? But we're going to use degrees. And a lot of times direction in our problems are given in terms of bearings. So if, say, the direction is 30, in the problem is given as 30 degrees south of east, or what did I say? East of south, sorry. Like here, we're not going to put theta is 30 degrees. It's got to be theta is, 270 plus the 30 or 300 degrees. It's really important that you get theta in the right quadrant, because once you take the, use trigonometry, that affects the sign. All right, well, okay, so how is this going to work? So we're given in our problem the direction theta, and we're given the magnitude of the vector. And our objective is, can we figure out what the values of A and B are? Whoops, I have a little typo there. That ended up being bold. But of course that B is really just a real number, right? So it's AI plus BJ. Okay, so AB are the coordinates at the tip of the vector, because they're the components of our vector. So if we were, say we know these numbers, right, then we can use trigonometry here, draw a right triangle using the reference angle theta sub r, then and use a right triangle here. This would be the value of A, and this is the value of B. So the sine of theta is B over absolute value of V. And if we don't know B, but we know theta and V, we can just solve this for B. This implies that B, the vertical component, is equal to the magnitude of the vector times the sine of the direction of the vector. And then we can also show that the cosine of theta is A over V, right? So the x-coordinate of the point over R, like we called this R before, but that's the magnitude of the vector now. And so if we don't know A, we can solve, and if we know the magnitude of the vector and the direction, we can calculate the horizontal component. So that's what this theorem is saying. We're given the magnitude and the direction, then we can find the components of the vector using these formulas we just derived, right here and here. So you can use either notation, right? I'm going to usually use this notation. So this, of course, is A, and this is B. All right, so let's go ahead and do a problem. So U has direction 135 degrees and magnitude 10. So if we drew that in standard position, 135 degrees would be here, right? The reference angle is 45 degrees. So theta equals 135 degrees. This is 45 degrees. And the magnitude is 10, so the magnitude of U is equal to 10. So vector U is equal to 10 cosine 135 degrees I plus 10 sine 135 degrees J. So when you do this, remember the cosine is corresponds with the x value of, you know, the ordered pair that be at the tip. So it's always in the first component, sine in the second component. You don't want to mix those up. And this is, it's important you put 135 degrees in here, not 45 degrees, even though that's the reference angle, because you need to get the right sign. If you use 45 degrees, then you got to make sure you put a negative here. And so this is a special value, so you should be able to calculate this exactly. Cosine of 135 degrees is negative square root of 2 over 2. Cosine is negative in the second quadrant. And then sine is positive, so positive square root of 2 over 2. So 2 goes into 10 5 times. We get negative 5 radical 2i plus 5 radical 2j. And so what that is telling us, of course, let's see, what's 5 radical 2? It's about 7.07. You know, if we go back 5 radical 2 and up 5 radical 2, you know, that's the coordinates of these points, or of this point, excuse me, at the tip of the vector when it's in standard position. Okay, and of course you can use the other notation here. What I say though is, you know, if the problem is given, if the vectors are using IJ notation in the problem, then that's what you should stick with. And if they're using this notation, then stick with that notation. Don't go back and forth, just work with the notation that you're given. And sometimes you're not given any notation, then you have a choice, right? I like to use the IJ. Alright, so let's do a couple of applications. So in this first one, we have an airplane. It heads due north at 300 miles per hour. So notice that has a magnitude, 300 miles per hour, and a direction, due north. So that airplane, or that velocity, right, this is velocity, can be expressed as a vector. Then we have a wind blowing at north 30 degrees east at 40 miles per hour. So this can also be expressed as a vector. We've got a speed and a direction. So I'm going to draw these vectors, and this in part A it says express the velocity of the airplane and the velocity of the wind as vectors. So we have the magnitude and direction, we just need to find the components of the vectors. That's what we're really asked for in part A. Then find the true velocity of the airplane as a vector, and find the true speed and direction of the airplane. So what does that mean for part B? Well, what happens with the plane is set to go due north, and it's set at 300 miles per hour. The wind is going to knock it off course. So the true velocity, it's going to, the speed is going to be a little different, and the direction is going to be a little different. So in part B, we're going to express that as a vector, and then in part C, we're actually going to find the speed and the direction, you know, in terms of the magnitude, find the magnitude of the vector and the angle of the vector, theta. Okay, so let's go ahead and do all this. So part A, so we want the, we're writing the vectors, right? So for the airplane, I'll use A for the airplane, call it vector A. This one, you shouldn't even need the formula for if you understand what's going on, although you can use the formula. So I'm going to draw a picture here, and you'll see what I mean. So the airplane is going due north 300 miles per hour. So the magnitude, if this is vector A, the magnitude is 300. That's the length of this vector, right? This would be up 300 units. Well, you don't need trigonometry to figure out the coordinates at the tip. It's just going to be 0, 300. So you can do 0, 300 using this notation, or 300J. So this is the one I'm going to use here. Right? It's 0I plus 300J, but then we don't write the 0I because that's 0. But you can do, for the airplane, the magnitude is 300, the direction is 90 degrees. So you could do 300 cosine of 90 degrees, but that's 0. 300 sine of 90 degrees, sine of 90 degrees is 1. So you don't need to do that because you can figure those coordinates out without using trigonometry. For the wind, it's a little harder because it's not going along an axis. The wind is blowing at north 30 degrees east, 40 miles per hour. So the length of that vector is going to be relatively short compared to the 300 I have here. And north 30 degrees east, we would measure 30 degrees from north. So here's 30 degrees from north. So here's the wind, right? It's a pretty short vector. Now, the magnitude of the wind is 40. And then the direction of the wind, I'll just call it theta, so W, is not 30. You have to measure from here. It's going to be 60 degrees. And that's really key. That's where a lot of people mess up. That'll get the wrong components if you use 30 degrees. So the wind is 40, take the magnitude 40, cosine of 60 degrees I plus 40 sine of 60 degrees J. I'll just use IJ notation now. So 40 times 1/2 I plus 40 times the square root of 3 over 2J. So 20I plus 20 square root of 3J. These numbers are the ordered pair at the end of the vector. Okay, so this is what we're talking about in part A when we say express these things as vectors. You want to find the components of each vector. We're done with part A. Part B, find the true velocity of the airplane as a vector. Well, the wind comes along and knocks this off course, and what happens, I'm going to erase this 300, is the vector, or the length of this vector, if you translate it up here, right, this is I guess A, and this is W. It gets knocked off course. This has to be the parallel to the position vector, of course, and the sum of these two vectors, A plus W, is where the airplane ends up. So for part B, you want to find vector A plus W. And this is as a vector. So you're just adding the components of each vector. So A plus W is 300J plus 20I plus 20 square root of 3J. So 20I plus 300 plus 20 radical 3J. So those aren't like terms, I can't simplify that, but I could approximate. So this has the same, notice the horizontal component's the same, right? That was the wind, original wind, but then the vertical ends up being the 300 plus the vertical component of the wind. Okay, then C. So this is where the plane ends up. Find the true speed and direction of the plane. That means the speed is the magnitude of the resultant vector a plus w. I should write that down. That's the resultant vector. And then the direction is the angle. Of a plus w. And the direction, you can just state it as theta, a positive angle between 0 and 360, or you might be asked to use bearings. You should be able to do both. Okay, so the speed, so even though the instruments are set to go 300 miles per hour, because the wind is a little bit to the back, notice a plus w is longer, it's actually going to go a little faster than 300. The wind's helping it along. So the speed is the square root of 20 squared plus 300 plus 20 radical 3 squared, which is, let's see, square root of, plug this in the calculator, so 20 squared plus 300 plus 20 radical 3 squared, and then square root of the answer. I'm not even going to put this here. Just erase that. So that's approximately 335.2 miles per hour would be the units of the speed. And then the direction, how do we find that? And we'll just find theta. So when I'm writing theta here, I'm talking about this theta. And so notice what we can do is use a right triangle. The tangent of theta should be opposite over adjacent. And the opposite will be the vertical component of vector a plus w, and the adjacent will be the horizontal component of that vector. So note that the tangent of theta, here I'll draw it here, so if this is a plus w, this is 20, and this is 300 plus 20 radical 3, all right, and this is theta, so the tangent of theta equals 300 plus 20 radical 3 over 20. So it's going to be vertical component over horizontal, or b over a. And so theta will be the tangent inverse of this number. Now with tangent inverse, of course, if you're over here, you have to be careful because it's going to give you an answer over here, and then you have to translate it. Tangent inverse will give you an answer in either quadrant 1 or quadrant 4. But tangent is negative in quadrant 2 as well, so you have to be careful. Okay, so 3 plus 20 radical 3 over 20. That is approximately, of course, double check and make sure you're in degrees, unless you really want to use radians. But just as a general rule, we're going to use degrees in these problems. So approximately 86.6 degrees. If you're asked to use bearings, we would give this from the north line and be going to the west. So this would be north, let's see, 90 minus 8, the answer, 3.4 degrees to the east. Okay, so you should be able to do that if necessary. Now in your WebAssign homework, so I'm just using bearings here like we define them in nautical applications, but I'm trying to remember, because let me think. In flight applications, a lot of times bearings are just given from the north line, like you would just say 3, and you always go, sorry, I'm not super familiar with this. You always go in a counterclockwise direction, so it could be north 270 degrees, say. That means you're actually flying due west then. I can't remember exactly how this is written. Anyway, in your web of design, they do it like this for the airplane applications. Okay, so just keep that in mind, because that's important to make sure you get the right quadrant. That affects the signs of your components. Okay, so there's that one. Now let's do another one. So we did an application with velocity. Now we're going to do an application with forces. Forces have a magnitude as well, and force is applied in a certain direction, right? I could apply my force this direction. I could just push down into the table, and I'm applying a force even though it's not moving, because the normal force of the table is pushing back at me. Anyway, so the forces are balancing each other out in this case. That's why the table doesn't move, right? If I apply enough force, if I was strong enough, I could move the table, and then the forces wouldn't balance out. So, excuse me, and I apologize, I'm not the best at physics, so this takes me a little bit to think about. Alright, so our two forces in this case, F1 and F2, have magnitudes 10 and 20 pounds respectively. They're acting on an object, and they're acting in different directions. The first force is north 45 degrees east, and the second force is moving in north 30 degrees west. We want to find the resultant force, F1 plus F2, and then the direction of and magnitude of the resultant force. So let's draw a picture. Alright, so force 1, length 10, and it's north 45 degrees east, so here's force 1. And the magnitude of force 1 is 10, and this 45 degrees is measured from here, but of course that makes this 45 degrees as well. Then force 2 is twice as big, as 20 pounds, and it's north 30 degrees west. So we're measuring 30 degrees here. Try to make this look twice as long. Okay, so here's F2. Here's the magnitude of F2. It's 20. And these are in pounds. Forces are measured in pounds. And this is 30 degrees here. So that means the direction of force 1 is 45 degrees. The direction of force 2 is 90 plus 30, or 120 degrees. It's important, especially when you get outside of quadrant 1, make sure you don't give that as 30 degrees or 60 degrees, because the sine and cosine of 60 degrees are positive, and of course this vector, you can see it has a negative horizontal component, because cosine is negative. So you have to make sure you do 120 here. Okay, so we want to find the resultant force, F1 plus F2. So you can find F1 and F2 separately as vectors and then just add them up. So force 1 will be 10 cosine 45 degrees I plus 10 sine 45 degrees J. Force 2 is 20 cosine 120 degrees I plus 20 cosine 120 degrees J. Because these are special values, we can do exact numbers if we want, right? So this is square root of 2 over 2. And so it's this. So it's 5 square root of 2i plus 5 square root of 2j for force 1. Force 2, so cosine of 120 is negative 1/2. Whoops, I wrote cosine and this should have been sine. Excuse me. And then the sine of 60 degrees is square root of 3 over 2. So this will be negative 10i plus 10 square root of 3j. So notice, because we have the right direction, we've got what we need, a negative vertical component and a positive horizontal component. So force 1 and force 2 are working in different directions. The object, so they're both maybe pushing on the same object, right? Maybe the object is actually here. You've got this pushing this way and this pushing this way. It's actually going to end up, if you add these vectors up, so I want this to be equivalent to force 2, it's going to end up at F1 plus F2. So that's the resultant vector, the resultant force. So F1 plus F2 would just add up the components. So 5 radical 2 minus 10i plus 5 radical 2 plus 10 radical 3j. And we could approximate those. And that kind of gives you a better number sense of what's going on. So let's do it. 5 square root of 2 minus 10. Especially if your drawing's not that good, it might be hard to tell if this resultant vector ends up in quadrant 1 or quadrant 2. This will tell you. This is approximately negative 2.93i. So it is in quadrant 2. (24.39j). So it is in quadrant 2, and that's going to be important to know when you find the direction, right? So we found the resultant force. This is this question, right? I'll call it star. And then the second question, magnitude and direction. Magnitude, of course, we just do absolute, or well, not absolute value, but magnitude of F1 plus F2 is the square root of, so this number squared and when you do this, you know, if you use these numbers, just make sure you don't round these too much. You'll get a lot of round off error here if you round too much. So I think what I'll do is I'm going to use this number, negative 2. Oops. Actually, I don't even need a negative because I'm going to square it, right? 893 squared. That's accurate enough. Plus, and then use answer squared. And then the square root of that. About 24.57. Because these are forces, we'll label in pounds. Then direction. So again, we can use tangent. You can use any of the functions, but I like to just use tangent. So the tangent of theta, just make sure if you do this, you're using the right numbers, right? If you're going to use cosine, you're going to have to use the horizontal component, that's the adjacent side, and then the magnitude will be the hypotenuse, the length of the hypotenuse. But just in general, theta is tangent inverse of b over a, and use that pattern, right? So this is really close here. Let me just draw a new picture. So it's, if this is f1 plus f2, then we're taking the, and this is A and this is B, opposite over adjacent. That's where I'm getting the B over A, right? And those are the components of the vector. So tangent inverse of 5 radical 2 plus 10 radical 3 over 5 radical 2 minus 10. Now again, you can use your decimal numbers, but don't round too much there. So tangent inverse, what were the numbers? So 24.39157 divided by, the sign matters here, so don't leave it out, to, well, you can, but just be careful, make sure you understand the adjustment you need to make if you leave it out. Whoops, -2.92893. Okay, so about 83.2 negative. So here's where it's tricky, because you can't just use this. That's not the true direction. In fact, I shouldn't even call it theta. So theta, because this angle is down here, right, this is negative 83.2 degrees, so we're going to have to add 180 degrees. And then plus 180. 96.8 degrees. And of course, if we were using bearings, we would do north 6.8 degrees west, because we're 6.8 degrees past 90. Okay. I think that's all I have to say. Just be, you know, and again, I use tangent inverse here, but you could use cosine inverse. And the nice thing about cosine inverse is because this is in quadrant 2, it'll give you the right answer. So you would do the, for cosine, you would do adjacent over hypotenuse. So you'd use A over the magnitude. I'll show you what I mean. So I didn't have anything else to say, but I just found something else to say. So I'll just use this. 5 radical 2 minus 10 divided by the magnitude 24.5, well, let's use this, 6679. See that, and that gives you the right answer because cosine inverse comes out of quadrant 1 or quadrant 2. You know, and if your vector ends up in quadrant 3, no matter what function you use, you have to make an adjustment. So be careful with that. You have to understand those inverse functions. Some of you didn't understand that on the test, so you need to go back and review that. Where the answer is going to come, you know, where you're going to get answers isn't necessarily where the vector is. So you have to be careful.